Hello and welcome back to Elementary Algebra, section 5.1, Rules of Exponents. So we're going to deal with polynomials and factoring and a whole bunch of this stuff that involves exponents. So before we go and do any algebra, first we're going to deal with some basic computation, which is the part of the previous course, but I like to review anyway. So when you say, let's say a cubed, that means a times a times a. The number, which is called the exponent, tells you how many times you need to multiply what we call the base number. So if I have 10 to the fourth, that means it's 10 times 10 times 10 times 10, which is 10,000. 4 zeros. So we had 4 tens. Now, as you can see, 10 to the fourth is not the same as 10 times 4, right? 10 to the fourth is 10,000, and 10 times 4 is 40. So do not confuse those two things. Exponents and basic multiplication, they are not the same. So now, armed with this knowledge, we still need to talk about sign numbers, which is really confusing to a lot of people. Signed numbers have the rule with the exponents, have a quick rule, or you can just go, pair by pair and go that way. But signed numbers are going to be something like this. If you have a negative number raised to the even power, result is always positive. Why? Well, if it's an even number of negative a's, every pair of negative a's creates a positive. So if I have, let's say, negative 2 raised to the fourth power, that's 4 negative 2's. And as you can see, each pair makes a positive number for the total of a positive number at the end. So when you have even a number of exponents and you're computing, you are going to run into always you are going to have a positive number on the other end. Now, if the number is negative and the exponent is odd, you will have negative answer, because you will always have odd number of negative signs. So if I, let's say, go negative 2 to the fifth power, that's negative 2 times negative 2 times negative 2 times negative 2 times negative 2. See, this pair gives me positive 4. This pair gives me positive 4. But this one stays as negative 2. And the result is negative 32, right? 16 times negative 2 is negative 32. So what we have learned here is something that, you can remember if you want to, but you can also use the method that I use, that I say, where every pair of negative numbers, right? Every pair of negative numbers is giving me a positive. So if I have odd number, I can't make pairs with odd number, because there will always be one left over. And that's the one that would make everything negative in the end. Again, these are all skills from the previous previous course from arithmetic, where you were supposed to compute positive and negative signed numbers. So now we are going to take a look at one more rule, and this rule, it seems to be opposite, but it's not. It's actually just the deal here is that the negative is not grouped with the number, and then PEMDAS applies exponent before subtraction. It's a little bit confusing, but these are the two rules that you have most of the time. But sometimes you don't have those parentheses, so it's not only negative a raised to the even exponent. And in that case, it's a negative answer.
So when there's no parentheses, it's a negative number.
And we can do the calculation to see why. And again, if it's like this and it's odd up here, it's also going to be a negative number. Now we need to understand why are these without a parenthesis. So first of all, let's agree that on the number line, right, with a 0, we have positive numbers on one side and then the negative numbers on the other side. So we immediately, just because they're at different locations, we immediately understand that 2 is not the same as negative 2. They're completely two different values. One is right here, the other one is right there. One is positive, one is negative. So 2 and negative 2 are not the same. Now, when I want to, let's say, put negative 2 cubed, which is negative 2 to the third power, I get to write negative 2 times negative 2 times negative 2, which gives me negative 8. That follows the red rule over here with the odd exponent, trying to get the formula and the problem and the same screen. Yeah, so it's exactly this, right? So this one is that. Negative with parentheses, and as you can see, what I wrote here is negative in every single one of these factors. But now, if I write negative 2 cubed, negative is not cubed anymore. Negative is not impacted by the power anymore because it's not grouped with 2 anymore. Now, this is the only pair, right? You copy the negative and then you have 2 times 2 times 2. It still gives you negative 8 like before, but that will change for the even powers. But I just wanted to make sure that you understand the difference, visual difference between the two. So in this sense, you have like negative times positive 2 times positive 2 times positive 2. And the reason for this is PEMDAS. So this is not some arbitrary rule that someone placed, put down for you to memorize and then to confuse you or something. Over here, minus 2, negative and 2 are grouped with parentheses, and then you use exponent. So negative is grouped with the 2, and that's why negative shows up 3 times, because negative was assigned and associated with 2, and together they were cubed. But in the second example below, you don't have that situation. What you have here is 3, which is the exponent, is applied only on a number 2, and then the negative in front is the one that you can copy. If it's going to make you happier to write 0 minus all of this, you can, right? There's no reason for it, but you can. And now, when you take a look, this cube, the exponent of 3, is going to make 2 repeat 3 times. Earlier, it was negative 2 repeating 3 times because you had negative associated with the 2. Now, negative is no longer associated with 2. It's associated with the entire problem. So you can literally put these parentheses around like that if you want to out of nowhere, and you can see that 2 cubed is what we have in this parenthesis. Now, even if you don't know this, just because you're getting the correct answer, you kind of can get away with it. Now, where it really shines is when you say negative 2 to the fourth. In this case, you have negative 2 times negative 2 times negative 2 times negative 2, which altogether is 2, 4, 8, 16. Positive 16. See, the pair gave me a positive there, the pair gave me a positive, so those are positive 4s, and now when I multiply two positive 4s, I get the positive 16. And now we're going to contrast that with this. Now, if you don't do it correctly, right, I will know that you don't understand these rules. Because now, again, the 4 only applies to 2 because exponent before subtraction. So we copy the negative, and in parentheses we have 2 times 2 times 2 times 2, and this works out to be negative 16. So these are not arbitrary rules. These are rules that are well understood, and you decide whether you want to study them and learn them, right? Figure them out, or you want to ignore them hoping they will never show up, which they will, you know, in your next course, for instance, when stakes are higher. So we see the red rules, this one and this one, and we see the blue rules, this one and this one, and you see how they differ. This middle part over here is the most important, obviously, because that's where the understanding kicks in. Like, what do you repeat 4 times or 3 times? Is it the entire number, negative 2, or the negative is not included in the parenthesis with the value, so you can just copy it? So those are some basics of computation with exponents and worrying about those signs. So now you have the rules for addition, subtraction, multiplication, division, and now finally for exponents. And you can compute literally anything. It's worth mentioning, it will pop up also. I actually did before. I remember a couple of problems we did in chapter, I believe, 1. If you have a fraction, 3/5, let's say, and you square that, that just means 3/5 times 3/5, which is 9/25. So it's very easy to write this fraction twice, multiply the numbers, which is just go across. So 3 times 3 is 9, and 5 times 5 is 25. And then you move on. So if you have a fraction, you don't care. You can still compute, because the fraction can be written as 2 fractions, and then those 2 fractions would give you whatever answer you get. How about negative 2/7 squared? Can you tell me, are you expecting positive or negative answer? So just unmute and say it, and why. Why do you think so?
The negative.
Why would be negative?
Oh wait, no, sorry. It's an even, right? Right?
It is even.
Because was it the parentheses, right?
But
And the
parentheses
negatives outside.
Yeah, parentheses. Yes, negative is outside. What do you think? How many negative signs do we have when we write this down? When we write it out?
1.
1. Very good. Yes. So we copy the negative, and then we have just 2/7 times 2/7. which is negative 4 over 49. So we only have one negative because it was not included in the parenthesis. Now, if I had negative 2 over 7 squared, then it would be negative 2 over 7 times negative 2 over 7, which would give me positive 4 over 49. So be careful where that negative is. Right? Is it inside or outside? Because the rules don't apply different. And I mean, rules. You don't need to know the rules if you do this every time. You don't have to clutter your head with rules if you are not lazy to write it out and then just use the basic computation. So you can either learn the rules very well, then skip working the homework all the way and all of that kind of stuff, right? Because you just know, right? You didn't have to do a lot of homework to memorize the rules because you just say, okay, I'm going to write it out every time. But you can also remember the rules. That's it. All right, so let's take a look at this new algebra stuff. B raised to the 0 equals 1 for B that it's not 0. So this is one of the rules that you have. And now these rules, you can't reason with some of them. You just have to know them. Eventually, you might stumble upon the proofs and derivations and all of these things, how they come up. But in general, in algebra, right, we don't do those proofs. So what I have here is that any number other than 0 raised to a 0 will give us 1. So that's 3 to the 0 gives us 1. 100 to the 0 gives us 1. Right? So all of those will give us 1. Now, to see this situation, you have to go to calculus to understand that. But in this case, when you just have any number other than 0 raised to a power of 0, you are going to have 1 as the answer. So that's the first rule. It's very simple rule. The next rule is going to be the product rule. And the way the product rule goes is if you have a raised to some exponent m and you multiply that with the a times to some exponent n, then those exponents just add. So you can combine those into a single problem and then solve only one rather than working those two separately like m and n. For whatever reason, you're doing these things. So this rule is very simple to use because it just involves addition of two numbers. So if you have x to the 6 times x to the 11, you are going to get x to the 17 because this 17 over here is 6 plus 11. That's what the rule said, the product rule, right? If you have the same base, and this is something that is very important, same base, you can, once you know, once you know that the base is the same, if you have the situation where these exponents are different, I mean, they don't have to be different. They're just, you have two factors with same base. In that case, you can try and compress them into the single answer, which is of the form when you add the exponents. So let's take a look at why cubed z times I just want you to add exponents, because if I do this, then I would have to factor. We don't do that yet. Let me just lift a couple of problems from the book, see what they have to say for this. So they say, how about you multiply y to the 7 times y cubed times y to the 0. What do you think the answer is? What do you think is the answer here?
Y to the 10th.
Perfect, but what happened with this one?
There's no exponent. Well, there is, but it's a 0.
Yes. So you would add it in as a 0, plus 0 in the exponent. You don't have to have only 2, right? You can have as many of these as you want. Here are other problems from the book. Again, if you don't like these problems, then don't tell me, right? Write the strongly worded email to the publisher. Okay, so we have the a squared b cubed times negative ab squared. Try that one. Come on, any answers? This is, I mean, you just need to add two numbers, so it shouldn't take a long time. Anyone? I guess still we are multiplying the ones that have the same value. So that's, oh, copy the negative, because positive number times the negative number is going to give us a negative. Okay, so that's positive times negative. So now what I have here, I have a to the 2 plus 1 times b to the 3 plus 2. That's all it is. So positive times negative number, and then a with
I'm
a
sorry,
and
how
b
did you
with b.
get a to the 2 plus 1?
What is the exponent on the first a?
2.
And the exponent on the second a is 1, because that's the
Oh.
base. Base is always 1.
1, okay.
Yep. So we have 2 plus 1, that gives us 3 by the rule, right over here, the product rule. And the other one, b, is 3 and 2, so that's going to be, when you add it, it's going to be 5.
Okay.
Cool. Trying to see if they have anything else like that, but I mean, all of these problems are very similar. I mean, I can make them up. For x squared y z cubed times negative y 4 z 4. So what would this simplify into? Can anyone tell me where should we start?
You distribute the 4 or at all or no?
Well, it's distribution is only when you have addition and subtraction, so 4 goes into each one. Now 4 belongs to the whole thing anyway, and this negative also. So we can start by kicking negative 4 out. This negative you can also perceive as negative 1. So negative 1 times 4 is negative 4. That's another way you can deal with that. And now we need to have our x, y, z with all of the exponents written on top. So x has exponent of 2. There are no other x to add anything to it, so we just leave it as is. Y, however, has 1 on the first and then plus 4 from the second. And z has 3 on the first and 4 on the second. Now I will explain why this works this way. 4x squared, and now this is y to the 5, and then z to the 7. 3 plus 4 is 7. And we are done. I'm not sure if you wondered why this works, right, without us actually going and working the terms out. Why does this, I don't want to dare calling it a shortcut because it's a rule of the exponents, but why does it work? So let's take a look at the very basic example of x cubed times x to the 4th. Now we know that the rule says add them and you get x to the 7. But if you write this out, this first, it has 3 x's in it, so x, 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 times, and this one has 4 x's in it. And these are all multiplied together. So all I get is 7 x's, which is x to the 7. That's why it works. Every time when you have this product rule, right, you can either know what you're supposed to add and subtract, or you can write it out in terms of these. Oh, I just made a face over here. I don't know if you see that. It's not too happy, but there you go. Anyway, when you get a problem right over here, you can write this out, you can write this out, and then you just count them all together. You're going to have 7. Now, obviously, knowing the rule helps a lot. Yes. Was that a question? I guess not. Okay. So the next rule that we are going to take a look at is the rule where we have exponent of the exponent. And this is called power to a power. Sometimes exponent is also known as power. And the rule is a to the power of m, to the exponent of m, and then all of that to the n is am times n. So in this case, you will multiply exponents. So if I have 3 squared raised to the 6, it's simply 3 to the 2 times 6, which is 3 to the 12. Now, what I want to contrast that with is 3 squared times 3 to the 6, which is 3 to the 8, because 2 plus 6. So we see that if you have the exponent of the exponent, they multiply, and if you have two factors separate, they add for their exponent. Now, obviously, for all of this, base needs to be the same. So how about 1/4 squared to the 8th power? Well, you know what to do. 2 times 8, it's 1/4 to the 16th power.
I'm sorry, can you repeat the last part where you said versus 3 to the second power? So I see what you have there, but you said if you're multiplying by the same base, you're just adding the
That's the old
exponent?
rule, yes. So this rule is the old rule where you have a to the m times a to the n equals am plus n. That's the old rule.
Mm-hmm.
Now the new rule doesn't have this repeated 3, right? It's 3 squared and then everything to the 6. So I'm trying to make immediately contrast between the old rule and the new rule, so you guys don't confuse that the two rules, like, oh, which rule am I going to use now? Because it's always clearly written one way or the other way. So now obviously you know, spending time figuring out which one is which, you know, and learning them is a different story. But what we are going to have here is you know, one way or the other way. So let's take a look at one more of this, but now we're going to use, let's say, variable x. I don't need to use 3 or 1/4. I can just put x for any.
So when do you add the exponents? Because you didn't really answer that question. So when do you add the exponents?
When you have multiplication.
So when you're multiplying,
yes,
you're adding the exponents.
Which was the previous rule, right? That was this one. Right, when the two are multiplied, and here is the example, x to the 6 times x to 11, 6 plus 11 is 17. The new rule is when you have exponent on top of the exponent, then you get to multiply exponents only. You still only have one base. Technically, some students also say, well, it's easy to remember because here you only have one base, meaning 1, 3, and over here you have 2 of them.
Oh, okay.
Right, so like, okay, fine. Now, going back to our current rule, if I have any variable, and that variable is, let's say, cubed, and then everything is raised to the 5th power, then it's the same rule. X 3 times 5, which is power of 15, or the exponent 15. Now, for those of you who wonder why this rule works, it's pretty much the same as, you know, it's pretty much same thinking as the previous problem. So let's say you have y to the 4th power and then everything squared. We said that that's going to be y to the 4 times 2. It's going to be y to the 8th. So, right, that's that. Now, what I want to do with this one is explain why this works. So, how many y's do I have? I have 4 y's. And that needs to be squared, which means that you have to multiply this by itself. So you get the first one, and then you get your second one. And if you look all together, you have 8 of them. So that's like a, in the background, why this, we can just multiply exponents. Even if you don't know the rule, you can still work it out, because now this is using the rule, and this is using street smarts. Huh? How about that? Street smarts. Because they get you to the same answer. This is technically what is happening in the background of the rule that you memorized. Again, when I have y to the 4, that's writing 4 y's multiplying each other. And then we still have this exponent, so we'll copy that. And then we know what the exponent of 2 does. If you have x squared, that means it's x times x. If you have a heart squared, that's just heart times another heart. So the idea is that no matter what base you have, when you have a square on it, it looks the same here, which is this one, as just multiplied this many times. So what do I have? I have this 4y's squared. Well, by looking at my little cheat sheet over here, I don't care if these are 4y's or this is a single x or it's a heart, can be anything. Whatever is in there getting squared needs to be written twice exactly the same. And then you say, oh, okay, now we can use our whatever rule and come up with y to the 8th. Now, when I say whatever rule, it's actually the product rule, because y times y, that's y to the 1 plus 1, which is y squared. And then times another y becomes y cubed, times another y becomes y to the 4th, and so on. But once you use up all the y's, you will reach y to the 8th. You're done, right? There's no more calculations. All right, cool. So that was the power rule, and I want to pick something from the book to see how well this works. Now I have to be very careful not to pick problems that are our next. We have 2 more rules after this. So the book has a z to the 7 everything cubed. If you know the answer, just say it right away.
Z times Z to the 21st power?
Yes, Z to the 21st power. Excellent. Oops. So this is going to be Z 7 times 3. It's Z to the 21. Awesome. Let's take a look at another problem. How about 3x squared times x to the 9? What do you think?
Three x to the 11th power.
Nice! This is me being an evil person, for the lack of the better word. And I tried to sneak in the old rule, right? So the exponents add in this case because we are multiplying 2 separate x's, right? So the exponents would add into 11. Awesome. Awesome, awesome, awesome. Now, one more thing. If you have something, you can combine rules. So you can have something like this. Negative 2 x to the fourth times 3x squared to the sixth power. So this problem is trickier because it contains, as you can see, both rules. And if you use PEMDAS, which is parenthesis, exponent, multiplication, division, addition, subtraction, you see that exponents have to be done first. And that's exactly what you have here. This is the one that has two exponents in it, so that's the one that we deal with first, and then we'll deal with the rest. So I'm going to copy negative 2x to the fourth times, I'm going to copy 3, and this becomes x to what kind of power?
12th, right?
Beautiful, 12. And at this point now, we have our old product rule, which is the product rule with the two x's, right? X here and x here. And then we have also these numbers in front. So how much is negative 2 times 3?
So a positive 6.
Careful, negative times positive is?
A negative?
Yep. This is just like multiplying negative 2 times 3 on the side. Has nothing to do with x's. X's are going to be in their own category, and these two x's have their exponents, and those exponents in this case add for a total of negative 6x to the 16th power. So we'll have this power here. Did we all? I'm going to go through this problem again. I'm going to go through this problem again because this problem has a lot of different features to it. So we have this to deal with first, and you guys did the excellent job because you see that's a power to a power, and that gives us 12. Then the next part is we have, now when we're here, we have our situation when we are supposed to add powers because we have two separate x's. But we also have these numbers in front. And those numbers are taken care of separately from the variables. So negative 2 times 3 is negative 6. That's dealing with just numbers, completely ignoring the x's. Now, for those of you who want to understand why we're allowed to do this, I will remind you of the commutative rule from chapter 1. Commutative rule in chapter 1 said this: A times B is the same as B times A. And you know that, like 2 times 3 is the same as 3 times 2, both give you 6. So commutative rule works. Now, how's that commutative rule applied here so we can do this stuff? Well, you see that this technically is negative 2 times x to the 4 times 3 times x to the 12. And I'm going to apply commutative rule to swap these two. So it becomes negative 2 times 3 times x to the 4 times x to the 12. So commutative rule is the one that allowed me to change the order of those two. And now here's my negative 6, here's my x to the 16, and then that gives me the answer we had. So this problem is a little bit, I guess, spicier. in some sense, but it's a good exercise to definitely make sense of the two worlds that we have. Questions, concerns, anything? No? Okay, let's take a look then at the next rule. And the next rule is going to be product to a power. Do I use the blue to write? Right, and then, yes. Product to a power. And if you just carefully read the title, product to a power. And this is, you know, people usually say, oh, you just distribute n. No, but yes. So distribution is done, it's multiplication, right? When you have a, b plus c, and you do a, b plus ac, you distributed a. It's not the proper terminology to be used for exponents, but technically, you know, each member of the parenthesis got their own n. Just like before, right? In the distribution problem, each member of parenthesis got its own a. So it's wrong to say distribute, but then everyone does say it, so whatever. And you can do this to more terms than two, right? So if you had can be done to any number of, not terms, factors. So if I am to have, let's say, a, b, c, x, y raised to the power n, then it's a to the n, b to the n, c to the n, x to the n, y to the n. So every member of the parenthesis will get its own power of n. Now, usually for the formula, we just use 2 to show the formula, but then we know. Now, obviously, you can't know if no one told you before, but we can have this for any amount of variables inside the parenthesis. Now, this is very useful because situation like this, like 3x everything squared, pops up very frequently in mathematics. And by the rule above, 3 gets its own square, and x gets its own square, so it becomes 9x squared. If you had this as a 6x squared, slap yourself to wake up, right? 3 squared is 3 times 3, right? Which is 9. 3 times 2 is 6. So those are completely different concepts. Negative 6x y squared everything cubed. Stuff like this is also very frequent. And it's only going to use the rules that we have, right? So the latest rule says, take this power 3 and apply it to every single member of the parenthesis. So I have negative 6 in parentheses raised to the 3. We say cubed. Then you have x cubed, and you have y squared cubed. So now all you need to do is to simplify this. This one over here is negative 6 times negative 6 times negative 6, which is 6 times 6 over here is positive 36 times negative 6 is negative 192. No, 196. 6 times 6 is 36. 6 times 3. No, I am so off.
I have a question. Why is the x not in parentheses?
216. 216. You can, because it doesn't have anything happening to it, let's put it that way. See, 6 has a negative that it's associated, so we learned that these two are different things. So we had to put negative 6 in parentheses because negative is grouped with 6 and 3 applies to all of that. So negative is the reason why you have parentheses in the first one. On the last one with the y, you have y squared and then everything needs to be cubed. So, first making sure that you know what the y square is there and then cube. Now for x, nothing special is unfortunately happening with x, so x did not get the parenthesis. It was just single x and then you apply cube on it, so there was nothing special happening there. So negative 6, and negative 6, that's 3 times negative 6. And then, as you can see, answer is going to come up negative when you multiply all of these values. So that's, as I said, 180 when you multiply 30 times 6. And then 6 times 6 is 36 when you add them, 216.
So a negative times a negative. Oh, I'm sorry. So a negative times a negative is a negative.
No, negative times a negative was positive.
So can you move the screen down so I can just see the answers? Okay, so negative 6 cubed, you got a positive 216?
Negative. Because we have three negative 6s. That's odd number. So the first two, I wanted to change the color. I already circled it here. So the first two gave me positive 36 because negative times negative is a positive. And then you have another negative coming in.
Got it.
So now positive times negative is negative. Yes. We cool? Awesome. And now, so that's that. And then x cubed, nothing special. So that we'll just copy that one. And what's happening with this y squared cubed?
Y to the 9th power. Oh no, I'm sorry. 9 to the 3 times to the 6.
6.
Y to the 6th
Good.
power. I'm sorry.
Yes. Y to the 6. And there we go. That's it. I don't need this either. So when you look at this now, we have to apply the power, in this case a cube, right, cube. Apply the cube to each one of these. And there they are. Each factor of the parenthesis got its own 3. Now I did say again, why is this one not getting parentheses? It's because there's nothing special happening to it. This one has a minus, which required a parenthesis. This one has a square that requires a parenthesis. So all of them require extra parentheses. And there it is. So now we actually don't need any of this stuff here. I'm going to leave it in for calculation, but this is our solution. Let's take a look at what book has to throw at us. So on page 319, they have a lot of these problems. How about 3a squared everything to the 4th? Okay, try that one. You can always say the answer. If you have the answer, just go ahead.
Is it 3a to the 8th power?
I am happy with a to the 8. I'm not happy with that 3. So the 4 is going to go to both of these. So we're going to have 3 to the 4 and then a to the 8, as you said, right? And 3 to the 4 is 81. So that's the right, because we did have, when you say 3a squared, everything to the 4th, you have two separate things here which are multiplied, which is our previous rule. You have two different things inside multiplied, factors, I'll say things, but factors. So you have two different things multiplied, and then each one of them gets its own exponent. So 3 gets its own 4, and a squared gets its own 4, so that's why it's 81. Let's take a look at more of these because they are so cool. Problem 48 says -3 r to the 4 t cubed everything squared. That's problem 48.
Is this one 9r to the 8th t to the 6th?
Perfect. Yes. I will write the intermediate step, -3, and then put a square, and then r to the 4, put square, and t cubed, then put square. And now they all have their own parentheses because none of them was single like earlier we just had x, right? They all have something happening. So now -3 times -3 is +9. And then we have r to the 8, and as you said, t to the 6, because 4 times 2 is 8, and 3 times 2 is 6. Cool. one more rule, which is the quotient of the power. I mean quotient to a power. And the rule is if you have a fraction, then each gets its own exponent. B needs to be not 0, but that's the detail about the fraction. It's not a detail about our algebra rule. Now, I did mention this before. Now I'm going to mention it again. 3/4, let's say cubed, is going to be 3 to the 3 divided by 4 to the 3. And you can actually compute this as 27 over 16 times 3, 48, I hope. 16 times 3, right? 48, yes. So this rule tells you that you have to give the exponent to each one, to numerator and denominator. So that looks like a fraction there. So let's take a look at some exercises to practice this. X over 2 to the 4th power. So write it out. And then if you can compute anything, compute. Anyone? This should be quick. X to the 4 is x to the 4. And then 2 gets its own.
32.
That's too much, I believe. I think there will be a 5. Because 4 2s, that's a 4, that's an 8, that's a 16.
Okay.
Yes, 16. Okay, let's take a look at the next problem. Now all of these are obviously directly from the book. Some of them are sneaky too. Oops. All right, let's take a look at 3y over 2 raised to the 4th power. Any suggestions? I guess not yet, huh?
Is that 81 y to the 4th over 16?
Yes.
And
Excellent.
then, no.
So we first apply the exponent to the numerator, and then we have 2 to the 4. And then we realize that this is the other rule where each one gets its own exponent. So now we have this, and that's exactly 81 y to the 4 over 16. Awesome. A squared b squared over 3, everything raised to the 5th power.
I'm sorry, how do we get the 81y4?
So we have to start then from the... guys, if you understand this problem, please work on this one, and I'm going to explain this problem here again. So this 4 applies to every single individual factor in the parenthesis. So the 4 applies to 3 and applies to a y, and 3 to the 4 is 81. So 3 to the 4 is 81 because, right?
Wait, okay, 3 to the 4 is 81. Oh, yes, the 9 and then the 9 again is 81. Right. Okay.
Yes, exactly. I was about to
Because
write
3
that.
times 3 is 9, and then another 9 will be 9 times 9 is 81. Okay.
Yes. Awesome. Good. And you
So I
do the
got the
same thing
81
with
on
2's
4.
on the bottom, right?
Yeah, so then 2 times 2 is 4, and then another, wait, did I do it right? 2 times 2 is 4, and then another 2 times 2 is 4. 4 times 4 is 16. Okay.
Awesome. Okay, let's take a look at this one. I'll give you a few more minutes. I mean, no one volunteered the answer yet, so keep going.
You.
Anything?
Is that A to the 10th, B to the 10th over 243?
Yes. Very good. So 5 will be distributed. Will be going to each one of these. And 2 times 5 is 10. 2 times 5 is 10. And then 3 to the 5. Now 3 to the 5, you can have 5 of them. There's your 9. There's your 9 and a 3. There's your 81 times 3. And now 80 times 3 is 240. And then plus 3, 243. Good. That's it, guys. That's the rules of exponents. So I'm going to put all of those rules on one spot. We have b raised to 0 is going to give us 1. We have a, m times an is am plus n. We have am raised to the n. That's going to give us amn. We have a times b to the n. So each one gets their own n. And finally, a over b to the n. Each one gets its own exponent n. So these are, let's go with the rainbow over here. We have to. We have to. Rows of exponents. And I am going to open the homework for this section. When you get a chance, hop on and do as well. You should do all of the problems correctly, because obviously the end of the semester, your homework grade is what you guys see in Canvas. No, in
Wait a minute.
Canvas.
That grade that's in Canvas, that's our homework grade, not the average grade?
No, sorry. I said the wrong word. When you are... I just opened the can of worms that I wish I could close now. I wish I could close this can of worms. So I have to explain the grades, the way. So Canvas will only have your exam grades. It does not have individual homework grades because it's just clutter. When your homework is done at the end of the semester, a single grade from MyMathLab, which is your homework average, will transfer into Canvas as a single number. So if you did all of your homework 100%, then 100 will be written in the special rubric that will open in grades in Canvas. So your Canvas is not tracking any of your progress on MyMathLab. Canvas will only have exam grades all the way through final exam. When you see the Canvas average, it's just the average of your exams. And then once you are done with the final, other grades will be added, like your homework and all of that stuff. So that's going to be all the way there. So now you just go and you follow your grade on MyMathLab for homework, and your exam grades, you follow them on Canvas. You have to log into MyMathLab. You know, someone told me earlier, well, you should link your MyMathLab grades to Canvas. Hell no, because it makes a lot of mess. Each individual homework becomes one column for you in Canvas. Then you can't find your exam grades because they're in between 40 homework grades. There's really no need for that. And you have to log into MyMathLab anyway to do your homework. So just check your grade if you care about it, right? Your homework grade averages on MyMathLab. And then when the course is done and over and the homework is locked, then that one grade, the average homework grade, will transfer as a single number, right? Ignoring all 40 individual homework assignment numbers, because, you know, all of them average into that final one. And that will be transferred to Canvas at the end, and that's it. So I hope I closed that can of worms and and just with the statement. So go to Canvas, look up your exam grades, go to MyMathLab, you look at your homework average, and then at the end, that homework average will make its way to Canvas to be calculated in a total average for the course, and that's it. All right, so let's take a short break. After the break, we'll do some exam 2 review. Exam 2 is coming up in 3 days, actually. So Friday, Saturday, Sunday this weekend. So we should do some review for that as well. So see you, I don't know, back in like 3 minutes or so.
Also on Thursday,